So we're just doing the first two sections of the prerequisites chapter. So today is going to be a little bit of a review. We'll move through it relatively quickly. So modeling the real world with algebra, section P1. So this is a picture of some of the aftermath after the Haiti earthquake in 2010. So what questions about this earthquake might we be able to use math to answer? Yep. Yep. Area damaged. Yep. What were you going to say? Number of people displaced. What else? Yep. Yep. Uh-huh. Correlation between the distance from epicenter and amount of damage. How do we measure amount of damage? Mm-hmm. Yeah. I think usually when you hear it on the news, they talk about it in dollars, amount of damage. Great, so lots of questions about a non-mathematical event that we can use math to answer. So a model is a mathematical representation, such as a formula or a graph of a real-world situation. We can describe, if you can describe the relationship between two or more quantities, you can write an equation that relates them. So this is an important step in problem solving, being able to convert a description of a relationship to an equation. So let's look at a model that we're all relatively familiar with, distance, rate, and time. So the model of distance, rate, and time of a moving object is that distance equals rate times time. So see if you can come up with one other model in your group, a mathematical formula that represents something in the real world, something like distance equals rate times time. So here's an example from your textbook of a mathematical model. A portion of a floating iceberg that is below the water surface is much larger than the portion above, hence the adage, it's just the tip of the iceberg. The total volume of an iceberg is given by this formula. So the total volume V is equal to 9.5 times S, and S is the area of just what you can see. It's showing. Okay, so if we want to find the total volume of an iceberg, if the volume showing is 4 cubic kilometers. So we start by writing down the model. And then you have to figure out which variable am I given here, V or S? S. So we replace the S with a 4. And 9.5 times 4 would be 38 cubic kilometers. And this time I want to find the volume showing if I know that the total volume is 19 cubic kilometers. So again, I'm going to start by writing down the model. And which variable am I given this time? V. So I'm going to replace V with a 19. Divide both sides by 9.5, and what do you get for S? 2. So only 2 cubic kilometers will show on a 19 cubic kilometer iceberg. All right, so moving on from modeling to the real number line. So this year we're going to spend time talking about solving equations and inequalities, and we need a precise and concise way to talk about solutions to these things. So we're going to talk about sets. A set is just a collection of objects. For example, you could have the set of students in this classroom, the set of blue cars in the parking lot, or the set of Oscar winners for Best Actress. So we generally write a set by listing its element between curly braces. So this is one way to represent a set. So if we let A be the set of the Three Stooges, then the mathematical notation for that would be A equals, in curly braces, Larry, Moe, and Curly. So if we let B represent the set of 7 dwarves, then what are the elements of B? Sleepy, grumpy, Doc, happy, sneezy, dopey. 1, 2, 3, 4, 5, 6. Angry? Is angry one of them?
No, I think Grumpy is angry.
Oh yeah, you're right. You're right. Grumpy is the angry guy. There's another one that doesn't end in Y. Oh, shoot. Bashful. There we go. All 7 dwarves. Written between curly braces with commas separating them. So the objects in a set are called the elements of the set. Name one element from set B that doesn't end in Y. Doc. Good. So the sets we're going to encounter in this class, though, are typically going to be sets of numbers. There are some other ways that we can write sets of numbers that are going to help us. Set builder notation is a descriptive way to write a set, and generally it looks like this. You put curly braces, and then you write the set, and you read it, the set of all x's such that, this vertical line is read such that, the set of all x's such that x meets some condition. Okay. So, for example, I could write this statement, and you would read that as the set of all x's. So the curly bracket indicates this is a set of things. This is the set of all x's such that x is less than 0. Okay. These are all the numbers. So this set is representing all the numbers that are less than 0 or negative numbers. So it's just sort of a fancy way of writing the negative numbers. So to talk about solutions to inequalities, we can use set builder notation. So let's say I write out the set of all x such that x is a solution to the inequality 3x minus 6 is greater than 15. Or more compactly, I could just write the set of all x's such that 3x minus 6 is greater than 15. So what elements are in this set? What numbers are in there? I'm looking for x's that make 3x minus 6 bigger than 15. 8, good. X is larger than 7. So we could solve this off to the side here. Add 6 to both sides. You get 3x is greater than 21. Divide by 3. And you get x has to be bigger than 7. So all the numbers bigger than 7 will make that statement true. So to write this in set notation, set builder notation, we write curly bracket for the set of all x such that x is greater than 7. It cannot, because it has to be 3x minus 6 has to be strictly bigger than 15. If you plug the 7 in, you would get 3 times 7 is 21 minus 6 equals 15. If there was an or equal to sign there, then we'd have an or equal to sign here. Yep. I don't, sorry. Oh, well, actually, there's these little tiny ones. Okay. Yes. All right, we also have a nice short way that's much more compact to write the set of points that are in an interval on the number line. So that are all the numbers between some number and another number. So for example, this says the set of all x's such that -4 is less than x is less than or equal to 1. So x here is sandwiched between -4 and 1, not including the -4 because there's no or equal to on that, including the 1 because there's an or equal to on that. So if I were to graph this, I would find -4. I'm going to put an open circle there because it doesn't include the -4. Then go to 1, put a closed circle because it includes the 1. And then this set is all the numbers in between. X is sandwiched between -4 and 1. So this is all the x's between -4 and 1. So it's just a graphical representation of what I wrote in the set builder notation. So if I wanted to write it out in words, I would say all the numbers between -4 and 1, not including -4, and including the 1. So it's kind of cumbersome to write it out in words. Set builder notation was a little bit of an improvement over writing it out in words. An even better improvement would be to write it out using something called interval notation. So if I want to put this more compactly, all the numbers between -4 and 1, I just write -4 comma 1. And you put a parenthesis if you don't include the endpoint, and a square bracket if you include the endpoint. So we say that the set is open at -4 and closed at 1. So this is a little bit of a repurposing of an old notation, right? Sometimes, so here's 2 comma 3. It's an example of a closed interval. It includes the 2 and the 3 and all the numbers in between. -1, 5 is an example of an open interval. It represents all the numbers between -1 and 5, not including either endpoint. Now this is where it gets it can be a little bit confusing because what does this look like? -1, 5. Yeah, it looks like a point. It looks like the coordinates of a point. So you have to be able to tell from the context if they're talking about an interval of numbers or if they're talking about a point. And it's usually pretty clear. So we'll see that several times over the course of this semester of repurposing old notation to mean something else. All right, how much time? Oh, we got time. Okay. So in your groups, I want you to graph each set. I've given it to you in Set Builder. I want you to draw a graph of it on the number line and write it in interval notation. And if you're stuck, raise your hand. I'll come around and help you. The set of all x's such that -3 is smaller than x, which is smaller than -2. Okay, so x is sandwiched between -3 and -2. So I'm just going to throw a -3 and a -2 on my number line here. And Both of my inequality symbols do not have an equal sign, so both of my circles are going to be open, 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 and then we shade all the numbers in between. And then this one, the set of all x such that 0 is smaller than x, which in turn is smaller than 5. So I'm going to put 0 and 5 on my number line. 0 is smaller than or equal to x, so I can include the 0. X is bigger than that, but smaller than 5. So all these numbers in here are included, but not the 5 itself. So then to write these in interval notation, since both of these are open, I'm going to use parentheses, -3, -2. And in interval notation, you always put the smaller number on the left, just like you would in a number line. Smaller number on the left. And this one, my 0 is closed, so I put a square bracket, 5, parentheses. So in general, whenever possible, we write numbers in sequential order. Smallest to biggest goes left to right, even in set builder notation. So we like to do that, even though, let's say, -3 less than x less than -2. It would be equivalent to say that -2 is bigger than x is bigger than -3. But because we rely so heavily on the number line visual to tell us about the order of numbers, it makes sense for us to always try to stick with that smaller number on the left, bigger number on the right. All right, you can continue working. If you finish this, you can go on to the next page. So I don't include the -3. What do you think about the infinity? Should I include it or not? It's not a number, right? Infinity is an idea of getting bigger and bigger and bigger, but you can't, no matter how long a number line I draw, I can't say, go up to that number line and point to infinity, right? I could ask you to point to 1 trillion, we just have to extend the number line far enough. But you can't point to infinity. It's not a number, so it's not actually included in the set. So now for the set builder notation, you start with the set of all x such that. And then I always like to, when it's an interval like this, I say, well, it's sandwiched. My x is going to be sandwiched. And so I start by putting the x in the middle, and then I put what I sandwich. So it's going to go from -1 to 2. And then you decide if you should add the or equal to signs. I'm going to put an or equal to sign on the -1 because it's a closed dot, not on the 2 because it's an open dot. So the next one's similar, the set of all x such that, and then I'm going to build a sandwich. 1.5 to 4. Both of the dots on there are closed, so I put or equal to signs on both of my endpoints. And then this last one, set of all x such that, I could go with my same approach here of creating a sandwich. Smallest number is -3, and the biggest number would be infinity. And I don't include either one. You can't include infinity, and the -3 is an open dot. Okay. But writing the less than infinity piece is not necessary, right? Because just saying all the x's so that -3 is less than x conveys the exact same information. And this is the one instance where I might break the rule of smallest to biggest left to right, because it might just make more sense to us in the language part of your brain to say this means the set of all x's such that x is bigger than -3. All the numbers bigger than -3, instead of saying -3 is less than all the possible numbers. So there's several ways you can write that one. All right, so now you guys seem to pretty much have it down. I'm gonna just do this one, set of all x less than or equal to 2. So here's a 2. All the numbers less than it would be numbers to the left. And I include the 2 because it's or equal to. And if I put this in interval notation, my biggest number is a 2, and I'm going to include it because you got to go left to right, smallest to biggest. What should I put on the left here? Yep, negative infinity. And I don't include it. Yeah, negative infinity because we're going to the left into negative numbers forever. All right, so let's go over using these to represent sets of numbers in a real situation. So what is the set of temperatures for which water is a liquid? Yep. 0 to 100. So I would say the set of all x such that sandwich my x between 0 and 100. Right? And should I include them? No? I don't think so, because I think 0 is the freezing point, right? So once you hit 0, you're supposed to freeze, and once you hit 100, it's going to evaporate. So I'm just going to put a little note here. We're doing degrees Celsius. What if it was Fahrenheit? Do you guys know what the numbers are? 32 to 212. Good. So if I'm going to write this in interval notation, I'm going to go from 0 to 100 and don't include either endpoint, so I use parentheses. All right, what is the set of heights that would allow you to ride a roller coaster if you have to be at least 60 inches tall? 60 to infinity. So I'll do that in interval notation. It would be 60 to infinity. Never include infinity. Should I include the 60? Yes, because if you're 60 inches tall, you get to ride. Yeah. And in set builder, this would be the set of all, I'll use h this time since it's representing a real thing, heights. The set of all h's such that h is bigger than 60. Or it might make sense to say the set of all h such that h is bigger than 60 instead of 60 is less than h. Or equal, yes, thank you. So this can get confusing sometimes for some people when you change the order. Just remember that the alligator always eats the bigger thing. Okay. I still think that after my 5th grade teacher taught it to me. I still use it to this day. The alligator eats the bigger number. So you're like, okay, h has to be the bigger, so alligator eats the h. Doesn't matter which order you put it in. Okay, how about the set of ages that are eligible to vote? 18 and up. Yeah, so if I do set builder, it will be the set of all A for ages, such that A is bigger than or equal to 18, because you get to vote when you are 18, right? And for interval notation, we would say 18 to infinity. Although in practical terms, there's probably some upper bound, right? Because we can't live to infinity, but however old somebody can live, they get to vote. So we'll put to infinity to capture that. All right, so at the end of each lecture, this is just a little set of things that you should be able to do after you go to the lecture, do the homework, and that some of these things are prerequisite things that we didn't talk about. They're in that blue packet. So you should be able to, after you do the homework, go through these and go, oh yeah, I can do all of these. Great. Okay. And your homework is in WebAssign. I want you to do the Intro to WebAssign assignment and the Class 1 homework.